Okay, welcome to lesson 6. This is learning target 5 on probabilities on the Z-score chart. So far we've only talked about Z-scores. I haven't really talked about Z-scores on the exception of a couple questions on exact values like whole number standard deviations. And so those are very helpful because we can say the idea 68, 95, 99.7. We can use those ideas when we're 1, 2, 3 standard deviations apart. The question becomes like, what happens if you're like 1.2 standard deviations apart? Like what if your Z-score is 1.2? What's your value then? Or if your value is a certain amount, what percentage are you higher than? That's really the question we're going to answer. What we're doing here is we've got to this lesson. It's really the big lesson in the unit, the big skill that we need to be able to do with normal distribution. And so we're going to kind of tie in together all the things that we've talked about already. So a warm-up question, say you know the area is under the normal curve. And we actually have a chart for that. It's in your textbooks. It's very accessible online, very easy. All you have to do is type in a normal distribution chart and it'll give it to you. So we've got the areas under the curve. So we know the areas because they're recorded, they're programmed into a calculator, they're in a chart. But you only know the areas less than a certain Z-score. So if you have a Z-score of 2, like we know that the area at less than 2, it might be in the chart. How could you calculate the area that a value is greater than a given Z-score? How about between two Z-scores? And so how would the questions be different if you only knew areas for positive Z-scores and you want to find the area for a negative Z-score? What it comes to here is the big thing is that there's symmetry involved in the normal distribution. So we want and there's also this idea that we add to 1. And so if we want the area greater than a given Z-score, we just find the one that's less, or we just find the area less and then subtract that from 1, or 100%. If we want the area between the two Z-scores, and if we think of like, if we've got the probability that we're 90, or we're less than the first one is 90, less than the lower one is 70, the area between is just 20. And so it's very, very quick to do that. We're just going to subtract the areas. And then how would the questions be different if you only knew the areas for positive? So if we know like that it's less than 2, for example, if we know that area, well, we know the area that we're less than negative 2 as well. Because the area that we're less than 2 is the area that we're greater than negative 2. We have the symmetry that's happening here. And so we can use the indirect method, the subtracting from 1, to actually figure it out. The learning target. And calculate probability that a specific data point lies within a given range. When we say given range, we don't always mean max min. We mean greater than a value or less than a value. And so we're going to see those 3 kind of ranges where we're greater than a value, less than a value, and between 2 values. We're also, and it should say here, we're also actually going to take a probability and figure out what the Z-score is for that. This is our normal distribution table. And so there's a whole bunch of values here inside. They actually tell you the area that you are less than a certain value. Recall that when we look at the area under a curve, we can calculate the areas more accurately by using a smaller interval. The only way we can get a really small interval is if we have a lot of data, very accurate, to analyze. The normal distribution, what it does is it assumes infinite data points, continuous function, so it actually can close the interval as small as we want. But we don't want to go too crazy with the size of the interval, so we use 0.01. 0.01 is a nice one because we can look at it's to the nearest hundredth. And so down the left here, we can actually look at Z values to the nearest tenth. And then out the right here, we can look at Z values to the nearest hundredth. If we go to the nearest thousandth, we almost have to have like another, have to have a lot bigger chart here. Okay. What the numbers in the chart tell us is the probability that the percent probability, the area, is less than the given Z-score. So all these numbers are less than a given Z-score. Okay. Looking deeper at the numbers, if the numbers in the chart were just areas of single bars that have a width of 1, the areas would be extremely small. So what I'm saying here is, like, these numbers here are not like the areas of a single bar between 0.00 and 0.01. It's all the area less than. So so at 0 it makes sense 50% is less than. We're just looking at things that are very, very small. And so I'm asking you here, like, although I won't assess this, but I just want to show you so you understand a little bit better. Notice the difference between each area of probability. Like, this is 0.5, this is 0.504, this is 0.508, this is 0.5398, this is 0.5438. How the differences areas increase, decrease for different Z-scores. And so up here, like, we're basically 0.4% apart. Down here, we end up becoming less than 0.2 apart. As we get further away from the average, because the normal distribution chart, because the added area for every 0.01 gets smaller every time, we actually notice that the difference in these numbers gets smaller as well. If you look in the bottom right of the top left of the chart, or the bottom right of the normal curve, there's very little difference between these numbers. And actually they're 4 decimals, and they can't actually, like, say what the difference is between these numbers, because you're just adding bars that are so small. Okay. Quick definition: probability percent area that is less than particular Z-score is called a percentile. So if a certain data point is higher than 81% of the data, it's called the 81st percentile. And so we just keep it simple, this idea of the percentile. If your probability is 80.81, it's the 81st percentile. This idea of higher than 81% confuses people, because they think, like, well, if you're higher than 81%, shouldn't there be 82% lower than you? Shouldn't that be 80%? And so, but remember, it's continuous data, so it really doesn't matter. You're not actually, like, there. It's just 81% is lower. So remember the formula for Z-scores. We've got that again. We're going to use this formula today. Just a couple examples. If we had a Z-score of 0.82, just reading the chart, I'm just going to use these numbers here. The chart's a lot bigger than this. If we have a Z-score of 0.82, percents below that number is, if we look up 0.82, so we go 0.8 on the Z value, and then over to the 2, get 79.39%. I would say that it's really helpful for students to just be able to see for 2 decimal places as a percentage. These are percentages. They're going to be quoted as decimals, but if you can read them simultaneously as percentages, it's really helpful. What Z-score is at the 82nd percentile? So we have to go to 82nd percentile. And so it's right around here, 0.8212 and 0.8186. This is actually, like, you have to make a decision here, like, where is it? And I'd ask you if you could see that this is 14 off 0.82, and this is 12 off 0.82, so it's really right in the middle is what we want. And so we want both of these ideas. So at 0.9, and then between 0.91 and 0.92 is 0.915. I really don't mind if you say 0.91 or 0.92, but 0.915 is probably a little bit more accurate. What percent of the data is above Z equals 0.91? So you can look up 0.91 and you get 81.86%. That's below. Don't forget that this is the percentage below. So to get the percentage above, we get 18%. So we subtract from 100. What percent is between a Z-score of 0.3 and 1.21? Well, we look up both of those numbers. 0.3 is 0.30, so 61.79, and 0.121, and it's just the difference between these two numbers, the percentage between. So we get 26.9%. An example, and this is really the kind of example that you'll have to look at doing both on the test and the exam. A machine produces parts that are normally distributed with a mean weight 1.2 kilograms, so that's a continuous data point. standard deviation of 0.1 kilograms. And so we ask ourselves a bunch of questions with that. You'll always be given an average and a standard deviation for these types of questions. You'll also be told that it's normally distributed. And so there we can assume that symmetry. We can assume that it takes the form of that chart. But we can't just plug in numbers. Like the chart doesn't say anything about 1.15 kilograms. By the way, sorry, this whole chart is on page 480 of our textbook. And it's also in this folder, so you should be able to get the chart pretty easily from me. Page 480 of the textbook, it's on there, or it's posted online. But the chart doesn't say anything about 1.15 kilograms. What you have to do is use the Z-score formula to translate things into Z values. So what we do is we take 1.15 and sub it into the formula. Subtract the average, divide by the standard deviation, and we get negative 0.5. If we look up negative 0.5 in the chart, we should get 30.85%. So the probability you're less is 30.85. What's the probability that you're bigger? So again, you want to look up 1.23. Always look up the number you're given. Subtract from 1.2 and divide by 0.1, you get 0.3. That gives us a number of 0.6179. That's not the number we want. We want to subtract that from 100. So the probability that we're greater than 1.23 is 38.21. And that we're between 1.05 and 1.32, we have to look up two Z values, or calculate two Z values. The first one is 1.2 for 1.32. And that gives us 88%, 88.5%. The other Z value is lower than the average. It's at negative 1.5. And that, as we'd expect, gives us a smaller percentage, 6.68%. And the difference between those two is 81.81%. Data point lying at the 80th percentile. If we look up the 80th percentile, we get a Z value of 0.84. Subbing in the points, like the mean and the standard deviation, we actually have to calculate x. We can calculate x by multiplying both sides by 0.1. So cross multiply the 0.1 out. And then add 1.2, and we get an x value of 1.284. Okay? So that'll be the kind of questions we need to be able to do. Some discussion questions that are interesting to talk about. Probability a specific data point lies between negative 1 and 1. There's another interval that has a probability of 68%. So there you can kind of like move it over a bit, but realize that you're getting more if you move the negative 1 left, and then you can just play with Z values and see like what are two Z values that are 68% apart. And so it's just an interesting thing to look at. What would be an equivalent interval to the big interval between negative 1 and 1? Because negative 1 and 1 is got the biggest chunk of the data. So if we slide those with two different Z-scores, we actually we'll probably have a longer interval. We've said that the probability of being an exact value is 0. How could you calculate the probability that you're very close to an exact value? And how does this number change when Z is closer to 0 or farther away from 0? So this is kind of going back to like if we take two Z scores very, very close together, 0.01 apart, they almost become 0 when we're far away from the average. When Z is close to 0, that means Z is close to the average. But like if we look at two Z values further away from the average, when we subtract them, we're getting pretty much 0, but not exactly 0. When you get, and then we saw like the smallest one, if you do just two Z values that are really close together, right near the average, they're about 0.4% apart. So you can like do the probability of an interval when you're very, very close to or probability of an exact value, just two values very, very close together. If you knew the percentile, the specific data point is, how could you calculate the Z-score, the specific data point, the mean, the standard deviation? what do you need to be given? And so that's the idea. If you have 4 things in the formula, you need 3 of them. The probability that a data point lies in a certain range is almost 0. What do you know about the Z-scores? Like, they're very close together. The probability that a data point lies in a certain range is almost 95. What do you know about the Z-scores? They're about 4 apart, give or take a little bit. And so it's 4 apart is 95%. So give or take a little bit of the 4 apart. So here's some practice questions to do, and I encourage you to practice the ones that give you like a mean and a standard deviation you have to calculate.